Welcome back, folks. We're going to introduce another method of circuit analysis. It kind of pairs nicely with mesh analysis, and it allows us to do a little bit more. So a lot of people develop a preference for one versus the other. With this method of analysis, nodal analysis, there are a few circuits where I really suggest that you use nodal analysis, and we'll get to what those circuits look like and why I think that's the case. But just like when we started out with mesh analysis, I want to look at how to use the output of the analysis first, because it's useful to us to at least understand where we're going with it. So I have a couple, not even problems, but I usually hand them out in class and have you fill them out in class, and we do it all as a group, and it's good times, but now I'm here and you're there. So we're going to do it this way. We're looking for node voltages in reference to ground, and those are going to be our unknowns in nodal analysis. So right now we're going to look at some handouts that I use, and we're going to assume that we know the node voltages, and then we're going to go find, for this video, we're going to go find voltages across other things using those node voltages. Okay, so let's take a look at that. And here we go. So this is a completely made up circuit. I don't care what's in the boxes, but we have some nodes and they're labeled. Our ground is labeled down here. Okay, so we have one large ground down here. And then node A is up here. So I labeled it with a dot there, but remember that the node extends until you hit a component. So it extends all the way up here. Okay, B is in the center here. Oops, drawing just a little bit. And C, again, extends all the way up there, even though I have it labeled down here. Okay, so these are what we call non-reference nodes. So you'll hear me say non-reference nodes a lot. And when I say that, I mean any node that's not ground, because ground is our reference. Okay, non-reference nodes are the unknowns. Okay, and that's what we're looking for. That's going to be the output of nodal analysis, our unknowns. And by non-reference, I mean, let's highlight that a little more. Not ground. Okay. So if we know the non-reference nodes, we have A, B, and C. And a lot of times we'll talk about the voltage at A. And so that'll be VA. We know that voltage. We know this voltage. And we know this voltage. Okay? And that was a notation that I think I had mentioned early on when we were talking about ground. When there's a single subscript, we're saying it's the voltage at A with respect to ground. And the voltage at B with respect to ground, and the voltage at C with respect to ground. Okay, so as I shake everything here, so if I know those three voltages with respect to ground, and I know ground, right? What's the voltage at ground? Hopefully you can answer that question. What is the voltage at ground? Well, ground is always 0 volts. Okay, if I know those voltages, how do I go find V1, V2, V3, V4, V5, and V6? And I think it's pretty simple, and I'm hoping by the end of this video you agree with me. Okay, so if I'm finding a voltage, V1, I'm writing a KVL. So I'll do it first as a KVL, and then I'll give you the quick and dirty simple way to write it. But you're still writing a KVL. You're ending up with an equation that is equivalent to a KVL. Okay, so we're going to use that same trick that we used when writing KVLs, where we can jump between points. But we can jump between points kind of in a really simplistic way, and I think we did one that was rather simplistic. If I'm looking at VA here, it's the voltage at A with respect to ground. So it's really here. VA is positive here with respect to ground, so negative down here at the ground. And now I can write this little loop just going around this way. Okay, so it is a KVL. So this is my KVL for VA. And I'm going to go, well, this one's plus and that one's minus, so I'm going to drop. I'm going to drop across V1. Okay, and then here I'm moving from plus to minus again. So I'm going to drop across VA, and I'm back to where I started. Like the simplest KVL you could ever write. And that's equal to 0. Okay, and then we just solve it for VA. VA equals negative V1. And that's how not to screw up the signs. There's a faster way. And it works out even with some of the other ones. But if you have to, go back and say, well, VB is really here, right? There's VB, and there's VC. So you can look at them that way. But I want to do this fast, and I want to do it accurate. And I want you to be able to do that as well. So here's what we're going to do. Our alternate method, let's go with green. Our alternate method is to look at V1, okay, and say what's connected to the positive side. Okay, ground is connected to the positive side. And you can even throw the plus there because it's connected to the positive side. Obviously, you don't need it, but there it is. What's connected to the negative side? So A is connected to the negative side, minus VA. Okay, and that's equal to whatever's over here. So that's V1. Okay, so 0 drops out, and we get negative VA equals V1, which we can, of course, multiply both sides by -1, and we end up with an equivalent equation. Okay, I'm going to do one more like this. I'm going to do the KVL, and then I'll do the quick and dirty method. It works. It works every time. Okay, so let's come over here and say I had VB labeled over here, right? It's the voltage at B with respect to the ground node, and if I want to find V2, I should say this is the KVL for V1, and this is the KVL for V2. Then I'm going to follow, let's grab a different color. I'm going to follow this path. I'm going to come up here and down around here. Okay, and I'm back to where I started, so that's a loop, and we can write a KVL around it. Okay, let me get my big fat head out of the way. Okay, so I'm going to go up VA. I'm looking at the white here, so this is plus and this is minus, so I'm going to go down V2. And then I'm looking at VB here, so I'm going to go down VB. And I'm back to where I started, so that's equal to 0. All right. So if we know VA and VB, V2 is the only unknown, and we can solve for that, right? So V2 equals VA minus VB. Okay, ready? The quick method, behind my head. I'm going to disappear. Ghost Dave. Okay, what's connected to the positive side? VA. What's connected to the negative side? VB. I'll throw the plus in there for now. And that's equal to V2. Okay, and it's that simple. These end up being equivalent. Look, they're just, the sides are swapped, right? V2 equals VA minus VB. V2 equals VA minus VB. They're equivalent. So it works. So you're writing KVLs when you do this. And I want you to at least be aware of that, because everything comes from the fundamental laws, KVL, KCL, and Ohm's law. If I haven't said that enough, I'm going to keep saying it. You're going to get sick of it. But I want you to realize that even though we have these little formulas, we have these quick ways to write them, they're not coming out of nowhere. Okay, super important to tie it back to those laws. Okay, so let's see. For V1, we found that it was negative VA, right? Yep, VA equals negative V1. Oh, I did that. I ended up doing that backwards. It's V1 equals negative VA. I had it correct up here. Here we have V2 is equal to VA minus VB. Okay, now we can kind of rock and roll a little more quickly. V3, VC is on the positive side, and VB is on the negative side. Okay, V4 is over here. I kind of like this one too, because it's VC on the positive side, and then on the negative side it's ground. And it's consistent, right? The positive term is on the positive side, just off the screen, and we're going to subtract whatever's on the negative side. It just happens to be 0 here, right? So a lot of times that little detail gets overlooked. It's still legitimate if you look at what's on the positive side, subtract what's on the negative side. You're going to end up with the right result. Okay, V5. Same deal with V5. VB's on the positive side, ground on the negative side. So that's just equal to VB. And then I got to scroll up. Sorry for all the scrolling. V6. Let's see. V6 has VA on the positive side and VC on the negative side. Okay, so VA minus VC. Got that right? Yep. Okay. Okay, so we've got to follow those labels. Look at how it's labeled in the problem and work from there. All right, so here's the same circuit, but let's swap some things around. In the one above, way up, that we started with, come on, right for me. There we go. This polarity was opposite, and we ended up with V1 equals negative VA. But in this case, we're going to say, well, VA is on the positive side, ground on the negative side, so it's going to be positive VA. So if we swap the polarity, we're going to have a sign change. It's really easy to mess it up, but if you always look at what's on the positive side, subtract what's on the negative side, you're going to be okay. Okay, what would be another one? I'm not doing these all. Let's do V6. If it was plus over here and minus over here, then I would get, and I'll write this down further, I would get VC, or V6 equals VC minus VA. Okay, so those polarities kind of define the coordinate system. Okay, they define which direction's positive in the coordinate system. So I'll leave the rest of these in the image for you to play with, and if we need to, we can talk about them in class or office hours or wherever. Talk to your friends too. That, you know, you can learn from your peers as much as you can learn from me. So I hope you're doing that when it's appropriate, not on exams. Homework, be careful with that. Anyhow. So I hope you're feeling a little comfortable with the idea that we're going to be finding node voltages, and we're looking for non-reference node voltages as our unknowns with nodal analysis. And then if we know those voltages, those node voltages, we can find any other voltage in the circuit. And it's pretty stinking useful. Okay, so the next video is going to be similar to this, but now we got to go find currents. Okay, and that gets a little trickier. So stay tuned and good luck.